Boa tarde, pessoal. Bem-vindos a este último seminário do nosso ciclo de seminários internacionais em materiais compósitos. Lembrando que esse aqui é um evento apoiado pela Associação Brasileira de Polímeros, pela MTS Sistemas do Brasil, pela Texiglass e pelo Instituto Senai de Inovação e Engenharia de Polímeros. E é claro, né, quem organiza o seminário é a Regional Sul da ABPOL. Tá? Bem-vindo todos e a todas. Não esqueçam de colocar ali no chat o nome e a instituição para a gente controlar a emissão de certificados. Eu vou explicar mais detalhadamente ao final. Para fazer perguntas, vocês podem acessar o Mentimeter, ok? E no final a gente vem com mais detalhes. Good afternoon, everybody. I would like to thank you, Fernando Cunha, to accept our invitation to present this webinar today. I'm glad to receive you here today. Thank you, Fernando. Now, I give you the word to our chairman, Professor Sandro. The word is with you.
Okay, thanks a lot, André. So I'm going to present our presenter of the day. It's Professor Fernando Cunha. He's a textile engineer master since 2012 from the University of Minho, where he acquired skills in multifunctional textiles, textile composites, and biomedical textiles, among others. Besides that, he's postgraduate in business administration since 2016 from Porto Business School. Currently, he's an executive director of Fibrenamics, international platform of University of Minho, an interface of University of Minho for the development of advanced solutions based on composite materials and fibrous structures, and also executive director of Science Trees, a spin-off of the University of Minho, which aims to convert the knowledge of generating research and development activities into high-value added products. Throughout his career, he has had the opportunity to work in several research and innovation projects in different areas, such as construction, automotive, textiles, architecture, defense, and medical ones, and as main technical skills acquired international reference companies. Including product engineering, smart and functional materials, and advanced structures, processing and analysis techniques in collaboration with national international companies. Moreover, he has gained expertise in industrial and management consulting. As a consequence of this professional career, he is author of more than 45 scientific publications on development of advanced composite materials, characterization techniques, compatibility of materials, among other topics, and holder of 4 patents. So, Professor Fernando Cunha, it's our honor, pleasure to have you here. And for this seminar, we are very glad that you could accept our invitation. So please feel free to start the presentation. And we'll talk again in the end for the questions from the audience. Okay, thanks a lot again.
Thanks, Sandro, for this kindly introduction. And thanks also for this invitation to be here and to sharing our knowledge about this natural fiber reinforcement with or polymeric materials reinforcement with natural fibers. Thank you for this invitation, and thank you also, André, for this invitation. So now I share my screen. I guess now I'm sharing my presentation. Yes. Okay. So for today, I will be discuss four topics. I talk a little bit about the Fibrenamics from University of Minho and the relation to the companies and how it's happened, and more than that, how we transfer the knowledge between the university to the society and the companies. After that, we talk about development trends, more in global in this global situation. After that, we jump to the trends in natural fiber composite. And last but not the least, we talk about some case studies about natural fiber was a polymeric reinforcement matrix. So, Fibrenamics, it is one of the most recent universities in the country of Portugal, in the north of Portugal. Is located in the north of Portugal and is divided into large campus, one in the city of Braga and another one the city of Guimarães. We are there in School of Engineering in Guimarães city. About the University of Minho, I give you some numbers about the performance about our university. Just highlight some numbers. One is the international students. We have more than 2,000 international students doing the master and the PhD work programs with us. We have more or less 1,700 PhD students, more or less 1,000 teaching staff like professors, like 645 non-teaching staff. This means researchers, people doing the research, scientific publication and work performing with transfer the knowledge between the science situation and to the society. We have 31 research units. This means research centers. These 31, 26 are classified that excellent or very good in the rankings. This is very important. The turnover is 72 million euros directly in the economy impact, and we have 6 interface units. The Fibrenamics is one of these interface units. This means to transfer knowledge between the scientific and to the society. So for that, Fibrenamics is an international platform in order to generation, recovering and transfer the knowledge between universities and companies. And the main goal and the main materials is materials based on fiber and composite materials. Our idea is we believe in this triangle, then be a society in order to put the challenges of the society, the requirements, universities to generate the knowledge, and the companies, of course, in order to transfer the knowledge to them, in order to create products with add value. For that, Fibrenamics are implemented and are divided in the 4 different areas. One is the intelligence, in order to identify opportunities in the market. And for that, we use, of course, the traditional tools that we have, like paper reviews, participation in the different important groups in the Europe and in the world in topics like natural fibers, defense, polymerics, and so on. But we have the digital platform in order to do a train mapping technology in order to see what happens in this field. After that, we transfer this opportunity, we create this opportunity and transfer this opportunity to the scientific group. This task group, the main objective is generation knowledge, scientific knowledge, and generation R&D projects. In order to, after that, we transfer this knowledge in product, transfer and create this knowledge into a product. And we do through the technology group. In our this group, this mission is to transfer the technology and also generation projects with the companies. This is more oriented to collaborate with the different universities, and this is oriented to collaborate with the companies. Of course, after that we need to complement the all value of knowledge, and the last group is oriented to the business in order to add value to the change and generation business in this topic. This methodology was recognized by the European Union, was a success case in the knowledge transfers between the universities and the companies in the last years. This is our team. We are nowadays 45 researchers in different areas like materials, polymeric, mechanical, physical, biological also. We have a great team with a multidisciplinary team in order to achieve the different challenges that we have. So we also have that new platform, a collaborative platform between the peoples and connect peoples working together. This is our website. Then you can search on website in fibrenamics.com. That are all information are there. About the Fibrenamics knowledge, we define some strategy topics that we've been work in the last years. One is the smart materials, in order to give some new functionalities to the materials, in order to put these materials in order to make different things, different smart things. One is the chromotropic materials, that materials then change their color in function of an external stimulus, like light, temperature, water, but the most important one is the electricity, okay? The change that colors about when you put electricity on this product. Another one is the self-sensing, in order to monitoring that the material, like the natural composite or something like that. And this is properties, the ability of the material to capture signal from conductive fibrous materials like carbon, stainless steel, conductive fibers, but also in the natural fiber we can put a coating into this natural fiber in order to that fiber are conductive also. And the last is the energy conduction, and this means that we put the ability of the materials, the fiber materials, to conduct energy and to release into the form of different things. Another topic is nano reinforcement. Nano reinforcement, that in this topic we are using nowadays carbon nanotubes, cellulose nanoparticles, nanoplates of graphene, also silica nanoparticles, in order to reinforcement polymeric matrices to increase the mechanical and electrical properties. And also reinforcement at nano and micro scale. This means we can create a composite with gradients of properties in order to achieve different properties, best properties in that product. Another topic is self-healing materials. This means the materials will have self-regeneration capacity. These materials that have the ability to repair matrix and micro cracks, preventing their propagations. We have two ways to do that. One is leakage channels. We put some matrix on that channels. And another one is to encapsulate a matrix into a microcapsule in order to put in the composite materials, and that when we have a crack, a micro crack, lead to the microcaps to rupture and consequent release to the healing agent. The last, of course, it is the hot topic of the moment, the eco-friendly materials, in order to reduce the weight of the materials, recycle the materials, and obtain biodegradable materials, of course, using natural fiber and biodegradable polymers. In the trends of develop, of course, in a world changing fast with high growth of world population and over exploration of the natural resources, new development trends are emerging, like CO2 emissions reduction, weight reductions for industrial revolution, Internet of Things, nanotechnology, green technologies like solar and wind, ecological materials, and biodegradable materials also. One of the indicators of these emerging needs is the overshooting day. Is defining it was the day in every year in which consumers of natural resources made available annually by Earth is exhausted. It means that most of us are actually consuming on the credit the available ecological budget. Brazil are there. This means that in July in 2018, in Brazil in July are consuming all the natural resources for this year. Of course, overshooting day is reached annually, increase early. Of course, this is not so good. And since like 1917 was the last year in which the ecology budget was respected below the red line. This is the zero. This we nowadays we expected are there, but not happen, of course. And this is by the year where we are consuming a lot of the natural and research materials. Of course, we need to considering natural concernings about the sustainability and the circular economy, the waste management and gains a new life. And it is not possible to think about the linear economy. This is not so good in the actual days. So we need to think about the circular economy. In order to repair, we need to recycle, refish, remanufacture, reuse, maintenance, and after that we dispose in order to energy conversion and landfill materials. This is what we need to be, and of course we use biologic parts also. Waste consumer and generation, actually about the 65 billion tons of materials are expected per year. At this rate, in 2050, it will be need research equivalent to 3 planets to sustain our way of life. It is impossible, of course. We can see that. So the idea is to keep a given research in circulation for as long as possible. It means design products, process, and service that optimize that use of researchers so that at the end of their useful life, they can be reused, repaired, or reprocessed. About that, in trends in natural fiber composite, of course, we see in different periods in the historical data, different things happen. So at this moment in the 6th wave, our hot topics, of course, is sustainability, bioeconomy, green chemical materials, industrial ecology, and nanotechnology. So for that, we need to see about the emerging trends in the global natural fiber composite market, which have a direct impact on the dynamics of the industry, include emergence of new application areas and increased governmental focus on the use of biocomposites. Just give you some numbers about this situation. In 2015, global natural fiber composite market size to reach like close to 6 billion by 2009, and the natural fiber composite market world $6.5 billion by 2021. So about the market trends, of course, the sustainability in order to put recyclable materials, renewable, biodegradable, and eco-friendly materials. This is the column from sustainability part. About the competitive edge, the price, of course, needs to be competitive like glass fiber or something like that. The legislation, of course, need to accompany these materials and put some extra price in non-ecologic materials. Processability, of course, the raw materials supply, the raw materials diversity, and the performance, of course, the lower weight is one of these in focus to the composite materials. The main application in until 2020 is, of course, automotive sector and the building and construction. The main region is the North America and Europe are the most based on the automotive sector, of course. And this is the fiber that use hemp flax, kenaf, jute, NPP, PA, PLA, and epoxy. Of course, this is not so good, but of course, this is the most polymeric that use on that market. In natural reinforcement was a polymeric reinforcement. Of course, we need when we talk about natural fiber and use this natural fiber in the composite reinforcement was a composite reinforcement. We need to talk about the composition about these cellulosic materials. And on these cellulosic materials, these materials are composed by three big materials. One is the cellulose. The cellulose is a linear polymeric composite of carbon molecules linked by a glucose units. So the cellulose is responsible for some mechanical properties. The hemicellulose is composed by non-linear carbonate hydrate molecules, and that is responsible for biodegradation, moisture absorption, thermal degradation, and some of mechanical properties. And the last, and the external layer of the cellulosic fibers is the lignin. This is responsible for this resistance and protection against microbial agents. This is some days is the problem between the compatibility to the polymeric materials. And during this presentation, we see some cases when we need to remove this lignin in order to increase the compatibility with the matrix polymer. Of course, when you have different range of these materials, the cellulose, hemicellulose, and lignin, of course, the properties of the fibers are also change with the different fibers themselves. In the properties of the mechanical properties like tensile strength or Young modulus, of course, they change also with different composition in about the cellulosic or the cellulose or the hemicellulose contained into the fiber. So Of course, the most important factors in the natural fiber composites is of course the low viscosity in order to impregnate the fibers. Another one is the homogeneity of this impregnation, the low moisture content, the good thermal stability, and the sufficient fiber weighting. Let's talk about this topic. When we combine polymerics and put in the natural fibers, use natural fibers to reinforcement these materials, we have immediately we have the one problem. The problem is the lower interface compatibility the fibers with the polymeric materials. Why this happens? Because of course the lignin, the outsider materials, is hydrophobic. So this gives poor adhesion, bonding to the materials. So for that, something happens in my screen. I don't know where is red lines come. So let's continue. So natural fibers and surface treatments like chemical and physical, we need to do these surface treatments in order to remove fats and what's partial extraction of lignin, in order to increase of roughness and wettability capacity of the surface. And here we have the drop water test in order to see the super hydrophobic materials and the hydrophilic materials. In the natural fibers, we need to give this behavior to the natural fibers in order to put the matrix into the fibers. So for that, in the surface treatments, we have the physical one, the chemical, and the biologic one. About the physical, we have thermal and non-thermal. And in the non-thermal, we have the atmospheric and vacuum. In the atmospheric, we have corona and DBD. In chemical, we have alkali and coupling agents. About the physical treatments, do not change the chemical composition of the fibers, but however, they change the structural and surface properties of the fiber, and they influence the mechanical bonding to polymers. In order to separate natural fibers bundles into individual filaments, to remove the surface contaminants, decrease the molecular energy at the surface in order to penetrate the polymer, and increase the surface roughness in order to create adhesion between the polymer and the natural fabric, the natural fiber. About the physical one, we can see in the plasma, in the charge energy release to the fibers. We can observe before the physical treatments. You can see here different materials there. You can see that. Different materials on that side. And after the physical treatments, we didn't have this, but we can increase the rugosity of these materials after the treatment. This is very important in order to create adhesion between the polymer and the matrix. In the chemical treatments, when two materials are in compatibility, it is often a possibility to bring about compatibility by introduction of three material that was properties between those and of the other two. Alkali treatment, breaking of the hydrogen bonds. Partial lignin is removal. Okay. Activation. After that, we need to activation the hydroxylic groups. and decrease of the individual mechanical properties of these fibers. So that forming of strong covalent bonds with the polymeric and the materials. We have two ways to do that. One is alkali treatments, another one is the coupling agents, to put some coupling agents in order to create a bridge between the fibers and the polymeric materials. And another one, the alkali treatments, we operated into a fiber in order to decrease of fiber diameter, increase the surface ruggedness, increase the reactivity stis, and increase the wettability capacity into the fibers. So in the chemical treatment, like you saw before, in the it is similar to the plasma treatment. You can see before the physical treatment, and after the treatment, you can see this difference. The fiber is more cleaning than before the materials. Of course, in terms of mechanical properties, one of aspects very important is the critical length. This means that there are a ratio between the length of the fiber and the way to put this fiber in order to give some good mechanical properties. Not so longer, not so short. This is a middle term of the length of this fiber. Of course, there are a formula in order to calculate this critical length. This is very important on the composite materials. We see before that influence. About the process in order to make these composite materials. We have different processes. One of is compression molding in order to put the matrix, to impregnate the matrix into a fiber based on the temperature, pressure, in order to have a good impregnation the matrix into a fiber. Of course, that was a disadvantage. High probability of large quantities of production. This is the disadvantage. Of course, in the plastic polymeric materials, we have the extrusion process. One of these advantages is a possibility to incorporate high quality of fibers and the efficient dispersion of the fibers into a polymeric matrix. The disadvantage is the high processing costs in terms of creation of mold or in order to make a composite. A vacuum infusion is also a possibility when just talk about the liquid matrix, like thermoset resins, more or less thermoset resins like epoxy, vinyl ester or polyester resins. And the advantage is a uniform distribution of the polymeric, minimization of excess materials. Disadvantage is the rate complex, the time consuming process because of the we expend a lot of materials in order to produce just one piece of the material. In case I bring you some case of study about the natural fibers composite project. One of that is we're running in the company sector in order to produce dashboards, seats, inserts, and interior trims and door panels to the automotive sector. We combine the polymerics with natural fiber and recyclable carbon fibers in order to promote more sustainability composites. And the main goals is the sustainability, recycle, and weight reduction. This is very important on the mobility sector. The main challenges is the combination of natural fabric with the polymeric materials is the use extrusion process. avoid natural fiber degradation in extruder, avoid the natural fiber damage in extruder, ensure good dispersion of natural fiber in the polymeric materials by extrusion process, increase of mechanical properties with natural fiber incorporation to enable the reduction of the polymeric materials, and maintain the possibility of thermoforming the samples with natural fiber without break. This is very hard to do because when you thermoforming, we give some shaping about the material. I show you some pictures and videos after in order to see the extension the materials. So for that we use we did with sisal and core fibers, and we know about the degradation temperature is 200 to 120 degrees. So after that, before we use the matrix, the TPO matrix, we need to do an alkali treatment in order to remove the lignin, in order to put some best properties, compatibility. And of course, the main objective is natural fiber with the composite. For that, we use extrusion process until 15% of natural fiber, co-rotating extruder. The temperature, range temperature operated is, we did in the 175, close to 200 degrees. A planar die and the calendar rotated at 75 degrees. And for that, of course, we characterize, we do some mechanical performance tests, tensile tests according to the ISO 527. This is the video. I guess I can show you. This is, we are extruding natural fiber. You can see that on the directly on the rubber, and you can see the natural fibers in this way in the industrial machine. Of course, the main challenges is to dispersion of the natural fiber. We have good dispersion of natural fiber in the polymeric material that you saw in these pictures. Preferential orientation of natural fibers in the direction of the material flow in the extruder, and without evident trend of natural fiber. We have different fiber, different morphology of fiber. This is core fiber. This is sisal fiber. In terms of tensile strength, we verify that the increase of tensile strength with the incorporation of natural fiber was we are expected. Even great increases of properties with the surface treatment application. Then you can see without treatment in the yellow and the blue with the alkali treatment, you can see the gain of properties, mechanical properties. In terms of Young's modulus, we increase the Young's modulus with the incorporation of natural fiber, and even great increase of properties with the surface treatment application, because we optimize this compatibility with the natural fiber and the polymeric materials. This is for the TPO, and the breaking elongation happens. The results we are expected, decrease the breaking elongation with the incorporation of natural fibers. Of course, if the tensile models and the Young's models increase, we need to verify the decrease of elongation, and even a great decrease of properties with the surface treatment application. So sisal and core reinforcement TPO without treatment, we can verify the less properties than we see in the alkali treatment that prove that alkali treatment is very important with the compatibility to the polymeric matrix and of course the mechanical properties. This is the final thermosetting process in order to shaping the plates we are produced in the extruder. And this is the movie. You can see in the vacuum, the materials didn't fail and didn't broken. And this is very, very hard to do these shapings in this direction and this in multiple direction, and the materials have a good performance. This is with different fibers, the back and the front of the materials. Another project is the pineapple composite and pineapple fibers. The potential of life fiber of Azorian's pineapple in reinforcement of composite materials. This project developed in a partnership with a company in the Azores Island, volcanic island, which is utmost region of the Portugal. This is a project we develop in the pineapples production. That company have 1,000 of leaf waste generation in the production of this fruit, these pineapple fruits, and we take these fibers in order in this vegetation in order to convert in the fibers. So the main objectives of this project is to study the potential use of leaf waste fiber of Azorian pineapple in reinforcement of composite materials to architecture and urban furniture components, recycle and transfer leaf waste of Azorian pineapple, value waste leaf extracting cellulose fiber, obtain the composite materials combining pineapple leaf fiber with polymeric materials, and determine main physical, mechanical, and microscopic characteristics. For that, you use this cellulosic fiber, and we use the bioepoxy resin. That resin is thermoset, but we have a bio part of this epoxy. Of course, this study are been in the we doing in the epoxy way, but of course we do in the same with the same case was I present before with the thermoplastic also material. So the first phase, we need to extraction of this fiber cellulosic material with drying in the oven, like 110 degrees, in order to remove the water into the fiber. After that, we need to milling and segmentation of these fibers and cutting mill, segmentation in the 500 microns and 100 microns particle of length of fibers. And after that, we apply a surface treatment with NEA hydroxide sodium. After that, we drying these fibers, so milling and segmentation, the cut fibers materials that you said here. And after that, we apply the surface treatment with alkali treatment. This is the FTIR characterization of lead fiber. We can see the typical FTIR spectrum of cellulosic natural fiber. Significant difference between the samples with and without hydroxylation treatments. You can see this is original one, the black one. You can see these peaks, but in different dried you can see without these materials. But not significant difference between the surface treatment times. So use the technique compression molding in order to mix different components, casting the mixture into the mold, curve process acceleration at 18 degrees 30 bars during 10 minutes and cooling at the room temperature until total cooling of these resins, and doing the different percentage of fiber, 30% of fiber and 50% of fiber, and with and without treatment. Then you can see some samples about these fibers, and do of course different characterization of these materials. We can speak more about that, but this is more about the characterization of the materials, like the methodology. And of course, we can see there are a trend to improve mechanical properties with an increase of natural fiber content B and C materials, and future increase with application of surface treatment. Of course, the effect of percentage of the fiber increase the mechanical properties with the increase of natural fiber. You can see in the line A and B. When you compare B to C and D to A, you can view the effect of fiber size, that increase of flexural strain with the increase of fiber size, of course. Effect of surface treatment application increase the mechanical properties with the surface treatment application, like B to D and C to A. You can see there the flexural strain, and sample D with the best mechanical properties of flexural strain and the Young's models. This is the best one with 50% of fiber, the big length fiber, and with treatment. About the density, of course, the effect of percentage of fiber increase of density with the increase of natural fiber content, remaining parameters without significant influence of the values of density. If this, we can expect that. And the water absorption tests, the effect of percentage of fiber increase of water, increase of the water absorption with the increase of natural fiber content due to the higher affinity of the fiber. And the effect of fiber size, increase of the water absorption with the decrease of fiber size. And the last surface treatment application, increase the water absorption with the surface application. This is the most image of the fibers, upper fiber lengths in the sample B compared to the sample C and A. Cleaner fiber surface and greater ruggedness in the samples D and A. You can see here D and A. You can see the difference between these samples, the rugosity of these polymeric fabrics, and tend to decrease the fiber diameter with the surface treatment application, sample D pointing to the light renewal of the surface. About the smaller fiber polymeric distance at the surface, with the surface treatment application, samples D and A, we can include a great compatibility between the materials. You can see here the compatibility to the materials. We have the less distance between the matrix and the fibers. It is very important. And this is the demonstrator of model demonstrator of these materials, like the urban furniture components using these composite materials. So about the conclusion of this project, feasibility to use leaf waste of Azorian's pineapple to extract cellulosic fiber, potential to reinforce composite materials, large fiber lengths, height fiber mass fraction, and application of surface treatment benefit the mechanical properties. And surface treatment application can promote the fiber cleaning and a better compatibility between the materials, and of course the potential obtained into the sector of architecture and urban furniture components. So this is my presentation. This is my sharing. Now I guess I feel free to respond in some questions.
Okay, thanks a lot. Thanks a lot, Fernando, for this nice presentation of natural fibers. Yeah, I do have some questions from the audience here, and we have a lot of time, so we can do all of them. The first one is about Fibrenamics, not directly related to the topic today, but he's asking here. The person is asking here about the chromotropic materials Fibrenamics is currently working on. If you're working on chromotropic materials.
Yeah, yeah. Of course, we have a lot of work on these chromotropic materials in order to put some intelligence and smart into smart materials, like to indicator to have some PA solutions or electric chromotropic materials in order to put lighting or the color change with these stimulus. But basically, we use different chromotropic materials based on the stimulus that we can achieve. Like if you want to change the colors with the temperature, you use the materials that then change the colors between a range of temperature. Or another one is when we put some light, the color change with this light. And we can use these materials like a sensor in order to give some intelligence to the materials.
Okay. Another one about Fibrenamics also here. Nowadays, is Fibrenamics working in developing products for sustainable energy generation?
Energy generation, yeah. Nowadays, we create the knowledge in the energy generation about we put some piezo materials. Then we can walk on the materials, and this walk generation a cinetic energy, and this cinetic energy we can convert in the energy and store this energy and use the different materials. Of course, this is technology that not yet have TRL maturity to put in some feasible product, but we can generation this knowledge, and we are working on this technology also.
Okay. All right. Now to natural fibers here. Someone is asking if innovative natural fiber composites technologies emerge as a purely scientific initiative, or how can public policy affect this process? How can public policy affect this process of making these composites, natural fiber composites, more technologically available or ready?
Yeah, I guess we need to jump in the second wave for these natural fibers. In the first wave, we concerned more in use these natural fiber themselves. We extract to the nature and use this natural fiber with the properties that we can achieve on the nature. After that, we change the DNA to these fibers. But I guess the next jump is to put some biologic proteins and agents to make some nanofibers, like to put the bacterial agents to make some natural fibers like cellulosic fibers. I guess this is the vehicle to the next level of the natural fibers. And this is the good topic to develop. Sorry, and we achieve that on the Fibrenamics. We use a scientific part in order to put these biologic agents to create and fabricate these fibers. And now we see the merging about the biologic part with the engineering part. And this is synergy, the future synergy these materials, of course.
Okay. Yeah, I think here he wanted to focus on governmental policies to help the composites, natural fiber composites, to go to.
Of course, this is the same. Yeah.
Yes.
This is the same question when you talk about the single-use plastic and use the biodegradable plastic. We need to put some taxes on this single-use plastic, then in order to decrease the consumer of the people, and of course, because the natural composite materials more or less tend to the price is more higher than the glass to the same properties. And of course, the people go to the more easy way, and the cheaper, of course. And we need to do some politics in order to tax these materials in order to equilibrate the balance between them.
Okay. There's someone here asking about if soy oil, it's in Portuguese, I'm translating now, but if soy oil could be used as a way to improve compatibility between polymer and natural fibers. Soy oil.
I guess this is the biologic agents in order to increase the compatibility to put that. Another one is another process, biologic process, is to put some microbiologic materials in order to remove the lignin, the surface lignin to the fibers, in order to do the same with alkaline treatments or something like that.
Okay, so I think from the audience, that's it. I've got two or three questions for myself. I noticed that you're focusing a lot on chemical treatments. I mean, especially sodium hydroxide and the alkali treatment and other ones. But do you think that the companies that are using natural fiber and composites, are they actually treating the fibers? Are they just doing some basic pre-treatment and using as it is, not to increase cost or not to generate a residue? No?
Yeah, depending of the application and the sector. If you think about the automotive sector, this needs to be. Why? Because we expected to obtain these mechanical properties. But when we talk about the sector of architecture, you not need so much mechanical properties, and the people didn't know not do this treatment. But when you look at when you look for properties, mechanical properties like automotive sector, the guys do it. This treatment needs to do.
They need to do. It's still worth doing. Okay.
Yeah.
Another thing is on those extruded films. What's the fiber length? The average fiber length that you get there? The extruded.
The length is 2 centimeters, 1 and 2 centimeters.
Centimeters or millimeters?
Millimeters.
Millimeters. Okay. 2 millimeters. And the fiber content, that I believe that you have studied the fiber content, and what's the, if you put too much, you're going to have problems there also.
Yeah, of course. This is the amount of this for this particular application. This is about the 4 up to 10% of the natural fiber. Yeah.
In weight.
In weight.
10%.
Yeah.
10% in weight.
Yeah.
It's low, right? It's low.
Yeah, it's low because up to this, the mechanical properties is not so good because the fibers didn't work with the reinforcement, but with the carg. Yeah. Like
filler.
Like a figure. Yeah, like a filler.
Okay. Okay. Well, now perhaps we do a more general question now, Fernando. How does the Fibrenamics, how is it is sponsored by the university or not sponsored at all? I mean, how's funded?
Yeah, of course.
It's all from the companies, or how?
Yeah,
how
it's all for the companies. We didn't receive some funds for university to work. We not receive. Our budgets and our grants come to the companies. The companies come to us with different requirements. Some of them, we need to develop new products or innovative products in this direction. Okay, and we help to define this direction directly with the companies. We look to the capabilities and the skills of the companies in terms of technology, of course, in technology skills, and see what we can do with this company. After that, we running a project. We have a chrono map with different activities, and run the activities with these companies. Our activities start with the market trends and the state of the art. After that, we put activity oriented to the design skills in order to make a project, the composite projects. After that, we running different activities from scientific part in order to develop a technology or the scientific knowledge about this topic. After that, we convert this knowledge into a product. We make a prototypes of products, and of course, we test this product in the real environment in use with the companies direct with use. And of course, we help to the promotion with the results in the fairs or in the public articles and something like that.
Are you being able to produce the right patents as also, or the companies don't want that?
Sorry, can you? I didn't understand.
Are you able to write patents as well? Or?
Yeah, of course.
Yeah.
In some cases, the company want to be publish a patent. In some cases, this not happens because the company prefers to keep the secret from this side.
Okay.
Yeah.
All right. I think we have the last just arrived this question from the audience here. When using cellulose fibers with natural rubber, what would be a better mechanism for adhesion? A better adhesion mechanism? How to improve the adhesion with natural rubber with natural fibers?
We didn't work most with rubber, natural rubber, just in the thermoplastic, biodegradable plastic, but didn't work with the rubber.
With natural rubber.
Yeah.
Okay. All right. Well, I think that was the last one. Well, I would like to thank you again, Fernando, for having accepted this invitation. I think we had a pleasant time here, listening to the development of Fibrenamics, and I thank you again. I'm gonna pass it to Professor André to finish with the last announcements there. Okay. Thanks a lot, Fernando.
Thank you.
Bye-bye.
Thank you, Sandro. Thank you very much, Fernando, for this very nice talk. I think that this initiative of Fibrenamics is very important to share the knowledge of the universe to community. Now I will speak in Portuguese. Bom, pessoal, estamos chegando então ao final do nosso ciclo de seminários. Parabéns a todos que conseguiram chegar firmes e fortes até esse 7º seminário, né? Durante essa semana e a próxima semana, a gente vai estar providenciando e enviando os certificados de vocês. Então, todos aqueles que persistiram, né, por até 4 ou mais seminários vão receber o certificado. Então, tenham um pouquinho de paciência, a gente vai enviar para vocês. Gostaria também de aproveitar esse espaço para agradecer de forma aberta aqui aos nossos apoiadores, a ABPOL, em específico ao secretário da ABPOL, Marcelo, e o Charles, tá? Pelo apoio. A MTS Sistemas do Brasil, um especial Obrigado aí a Melissa, que tem nos ajudado e muito durante esses 4 meses. Agradeço também a Texiglass e ao Instituto Senai de Tecnologia e Engenharia de Polímeros. E agradeço, né? Não poderia deixar de agradecer ao mentor, ao nosso chairman aqui, o galã dos vídeos, o professor Sandro Amico, que foi a pessoa que motivou, que trabalhou, que fez acontecer, né, junto com a Bpol Sul aqui, esse evento. Tá? Então, muito obrigado, Sandro. Sempre bom contar contigo nessa parceria. Agradeço a vocês também. Tá? Então, fiquem ligados ali nas nossas redes sociais da Bpol Sul para novidades. Não sei se o Sandro quer falar alguma coisa. Poderia voltar, Sandro, para se despedir da galera. Eu deixo aqui meu abraço a todos.
Estou sob o impacto do que você falou. Tá bom, tá bom. Bom, eu só tenho a agradecer também a parceria da Bpol Sul. Quando eu contactei o André, foi imediata a parceria, e foi muito fácil trabalhar com o André. Estou muito contente. Estamos planejando alguma novidade para o ano que vem, né? Mas ainda estamos organizando, tá? Mas devemos fazer alguma coisa diferente para o ano que vem. Vocês ficarão sabendo pelas redes sociais, já que eu estou ativo nas redes sociais, vocês vão ficar sabendo pelas redes sociais. Eu agradeço, sim, a parceria do Bpol Sul aí, e eu espero que a gente possa pensar num outro evento para o ano que vem, iniciando no ano que vem. Muito obrigado, André. Muito obrigado. E aos nossos patrocinadores, como você já falou.
Tá bem, então. Valeu, Sandro. Valeu, pessoal. Uma ótima tarde, um bom final de ano. Se cuidem aí, que a pandemia parece que não acabou ainda, não dá sossego. Um abraço, espero vê-los logo. Tchau.